So as I told you, technology scaling, it is related to technology enhancement, that as the years goes, so device become more smaller and smaller, and it is more efficient performance wise, as well as the cost wise also. The cost is reducing. So in that way, I told you that there is here it is mentioned. So I am able to show this thing. This is the graph shown, where it has been shown that this is the what is the length of the channel, that is 14 nanosecond. Previously it was 0.35 micrometer. Okay, now it is nanometer technology. So as the technology enhances, your device become more smaller and smaller, and that's why here it has been shown that is yellow by core supply and IO by input output supply. So here core supply, it's merely requiring 0.8 voltage, but at the outside for the operation or activating certain device, you can amplify it. So for that, it has provided IO supply as a 1.2 volt. So every time it is not possible that we are shrinking the device day by day. So it may happen at certain time it will be zero, and if that is zero, it is not possible to have a characteristic of that device. So beyond this particular 16 nanometer technology, there are another technologies coming. Because of that, your device will become more efficient, and it will be becoming more smart. Okay, so this technology scaling is related to changing the particular parameters of the your device, that is PMOS and NMOS, as we are considering here CMOS. So that way we are changing the values of the different parameters. Okay, so here you are able to see this is the diagram where I have given the notation as a W T, that is T oxide. This is what is the junction depth XJ, SiO2 thickness, length of the device. So these are the various dimensions are there. So we are just reducing or scaling it down by certain factor called as the S, that is scaling factor we have considered over here as a S. Here, as I have copy pasted, it is mentioned as alpha. So in many books you will be able to see it as a scaling factor as alpha or S. Okay, so this we have taken. I'm not going in detail again because already we have completed this. Now this is the main important thing, that is there are three types of scaling. As I told you, constant field, which is called as a full scaling. Why full scaling? Because in this all the parameters are scaled down. Means parameter like oxide thickness, W, L, XJ, that is junction depth, or we can say that voltages, whatever the voltage, V threshold, VGS, VDS, everything we are scaling down. So that's why it is called as a full scaling. But in partial scaling, what is happening? We are just scaling parameters like X, J, W, L, but we are not scaling voltages. The voltages are kept constant. Suppose I am having 5 volt as a VDD and device is shrink down, still we are keeping VDD as a 5 volt. But in constant field scaling, we are decreasing that VDD from 5 to certain value. So that's why it is called as a full scaling, and this is called as a partial scaling, where we are keeping VDD constant. So don't get confused in this field. Field means actual voltage or actual voltage drop across that point, and voltage means whatever VDD you are applying. That way you can just remember. So this is related to partial, and field, F for full. That way you can remember, so you can understand. So partial constant field scaling means full scaling. All the parameter you are scaling by the particular parameter. Lateral scaling, I told you, you are just shrinking the gate size, but that we are not considering because we are concentrating on these two types of scaling. Here the scaling factor is S, which I told you, and always it should be greater than 1. As I given the example that if you got the marks 20 out of 20, and just I want to give the marks from 10, so just I will be scaling down by 2. So your marks will be out of 10 will be 10. Out of 20 it will be it was 20, but after scale down it will be 10 out of 10. Likewise, always the scaling factor or S should be greater than 1. Now whenever L equal to length of channel, that already you know, L is the length of channel, this is without scaling. Whenever I have written L only, that is without scaling, and whenever I have written suppose L dash, so L dash means it is after scaling whatever the value of length, that is denoted by L dash. Okay, so what is L dash? So we have scaled down that L by parameter what? By parameter S, and that's why L by S is my new value of length, and that is called as a after scaling my length change to L dash, which is equal to L by S, and always this S should be greater than 1. Hope the things are clear in your mind. I'm launching the poll. Give the answer fast because I will be putting this poll for 20 seconds only, because I need to complete the syllabus today. Just give the answer rightly. In constant field scaling, constant field F for full, likewise, all the parameters are scaled down, only voltages are scaled down, parameter other than voltages are scaled down. Just read the question properly and answer. Constant field. I'm closing this poll, only 60% answered. So what is the answer as per your knowledge? In constant field, it is a full scaling, means all the parameters are changed. Okay, so answer is first, that is all the parameters are scaled down. I'm launching second poll. Which type of scaling is called partial scaling? Yes, again and again I'm repeating, same recurring link is there. Don't get panic that I have not got the link. Same link you need to use. I got the call now only that the link is not sent by me. So it is not like that. The same link is same. So I'm closing this poll. 73% answer. So what is which type of scaling is called the partial scaling? That is constant voltage. You are able to see this. Partial means constant voltage, where all the parameters other than voltages are scaled down. Okay. Again, same type of question, but asked in the different way. In which type of scaling voltages are kept constant? Voltages are kept constant. Don't get confused. Read the question twice before answering. I'm closing this poll within 5 seconds. 5, 4, 3, 2, 1. Stopping. So that 80%, 82% student have answered, and right answer to this is what? Constant voltage, in which voltage kept constant, but rest of the parameter are scaled down. Okay, so hope the things are clear. Don't get confused, because this is the confusing point, that is constant voltage, constant field, constant partial scaling, like this. Okay, so moving further without wasting time. So now here I told you that this is the what? Sorry, I'm able. Cane. Okay, nothing is written. Over here, you are able to see these are the various parameter, as I told you, in full scaling or constant field, F for full, likewise you can remember. So all the parameters are scaled down. So you are able to see after scaling, it is dash, L dash, W dash, TOX, oxide thickness, junction depth. I told you earlier, junction depth is means the depth of your N plus or P plus doping. VDD is also scaled down. Threshold voltage is also scaled down, and this also scaled down, but here it is scaled up. Why it is scaled up? Because to have a charge field relationship, there should be proper charges, otherwise how current will flow. So you need to maintain that particular thing to follow the Poisson's equation, and that's why you need to increase it by S. Instead of scaling down, you are scaling up. Okay, otherwise current will not be flowing, characteristic will not be followed. So after scaling, this is what is the value: L dash, W dash, TOX, XJ dash. Okay, now constant voltage scaling. Here all the parameter other than voltages are scaled down. So here you are able to see this W, L, TOX, XJ will be scaled down by S, but VDD and VT will be remain same. So we are not changing this. And here doping densities we have increased by S square. Okay, so that is the thing. Now next point. Okay, that question I will be asking afterward. So moving further, here what you need to remember. Some points you need to do by your own. Just what you are doing over here is that what is the effect of your field scaling or constant voltage scaling or constant field scaling on the parameter, how it will affect the things, that is current density, gate capacitance, linear current through the when the linear region is there. So what is the linear current that you need to find out. So first we are and concentrate over here very properly. So first point is that gate oxide capacitance. Sorry, oxide capacitance. So what is oxide capacitance? That is the capacitance of this oxide layer. So what is the formula for that? You should know formula so as to put the values in that. So Cox, it is defined by Cox. Ox is in suffix. So it is nothing but a permittivity of that oxide layer divided by Tox. Now, as you know that Tox you are scaling. Okay. After scale down, what is the Tox? That is Tox dash. And what is that value Tox dash? That is Tox by S. So we have scaled down Tox by S. So if I want to scale down or after scale down, what is the value of Cox? That is dash. Before scale down, it is Cox, but after scale down, it will be Cox dash. Equation is same. Just what we need to do while calculating for Cox dash, you need to put Tox dash. So here we have kept Tox dash. What is Tox dash? That is after scaling, what is the value of oxide thickness? So that is changed to this, and I need to substitute this value in this equation. So after substituting this particular value of Tox dash, what I got, that is Cox dash equal to S into Cox. Have you got it? Have you got this? Because same thing we need to replace everywhere. What we did, we are having value of Cox before scaling, and we know that value of Cox after scaling, which will be denoted by dash. Okay, equation is what you need to remember. This equation, what is meaning of Cox? It is nothing but a permittivity of oxide divided by Tox. Now after scale down, as we are scaling down Tox in the constant field, all the parameters are scaled down, so my Tox is also scaled down. So after scale down, what is the value of Tox? Is nothing but this. We are replacing this value over here, and after that we got the value of Cox after scaling is S into Cox. So what is the meaning of S into Cox? That is your oxide capacitance increases by factor S. Got it? If not, again I will be giving second thing. In this way only you need to go. So I'm not taking all the things over here, but we will taking something and some you need to do by your own. Now what is gate capacitance? How gate capacitance will get affected? Because of constant field scaling. In constant field scaling, all the parameters are scaled down, that you know. So here, what is CG? That is gate capacitance. Now this is your gate, and related to that capacitance is there. So equation for that you need to remember. How that come is not an issue, but this equation you need to remember. So CG is nothing but a Cox into W into L. Okay, what? Cox into W into L. Now if I need to find out effect of gate capacitance after scaling, so it is CG dash. Now if I need to find CG dash, I need to replace this by dash dash, Cox dash, W dash, L dash. So after scaling, whatever the Cox dash, that is SCox. So I'm putting SCox in place of Cox dash. What is W dash? That is after scaling, what is the width? That is W by S, because I told you that all the parameters are scaled down by S. So W is scaled down by S, so W by S. L will be scaled down by S, so L dash will be L by S. So these all values we need to place in this equation to find after scaling what is the effect of that on the CG, that is gate capacitance. So after substituting this value, what you got? This is the value, and finally you got this CG by S. So what is the meaning of this CG by S? That after scaling, that is the constant field scaling, my value of capacitor is decreased by scaling factor S. Previously it was CG, now it is decreased by scaling factor S. Here it is increased by scaling factor S. Are you getting? Just let me know in the comment box, because this is total theoretical. You know, you should know that equation also. By substituting that value, you will be finding out what is the effect of that scaling on the parameter. Are you getting? Going. So now here I can say my gate capacitance is decreased by scaling factor S after scaling. Now over here, what you are able to see, current in linear region. Now what is the equation of current in linear region? That is, it is dependent upon VTS, VGS, and VDS. So this equation already we have taken, so I'm not going further in more detail. So I have written ID linear, that is drain current in linear region is nothing but a mu n COX, that is written. Now, as you know, in constant field scaling, all the parameters are scaled down by S. So here VGS is also scaled down by S. So VGS by S होगा. So यहाँ पे VGS by S. VTN will be also scaled down, so it will be VTN by S. VDS will be scaled down by S, so VDS by S होगा. और यहाँ पे VDS square है, so according to that it will change. So VDS square by S square. So what you need to do, everything will you need to replace by scaling value. So here W dash, L dash, VGS dash, VTN dash, VDS dash. Likewise, we have written this equation in this way. As already we find out COX dash क्या रहता है? COX dash is nothing but S into COX. So we have replaced that over here. Are you able to see? Just concentrate, because if you miss this point, you will not be able to relate. So just we have replaced this COX dash by whatever value you got previously as COX. W dash is nothing but W by S. L dash is nothing but a L by S, because we have scaled down the length as well as the all the parameters we have scaled down. So all the scaled down value we are putting over here. After substituting this over here, what we got, that this one. So what we can say, what you comment over here related to current in the linear region before scaling and after scaling. Anybody can comment over here. After scaling, the drain current in linear region is scaled down by factor S. Is it clear? After scaling, constant field scaling, linear drain current in the linear region decrease by or scale down by factor S. Means आपका linear current क्या होगा? Decrease हो गया. Hope the things are getting. We are getting the things. Next, what is current density? Okay, so what is meant by current? Equation is mentioned over here. J is nothing but, which is denoted by J, is nothing but आप drain current ले सकते हो in the linear region or saturation region. Divided by area. Okay, so I have taken support linear, because already I have find out what is the linear region current determined by S. So I am replacing this particular drain current by S, that is ID linear by S. Okay, then what is A? A is nothing but a W by W into L. So I need to replace W by W dash and L by L dash. So after putting this value, what I am getting, A is nothing but A dash is nothing but A by S square, because substitute these values over here, you will be getting A as A dash as A by S square. Now after substituting this A dash over here, because for scale down I need to have A dash over here. By mistakenly I have not mentioned dash over here. It should be dash at this point. So what is A dash? Is nothing but A by S square. So we have substituted A by S square over here. And what is the current that we got? ID linear by S. So after putting this value, what we got, that is density, current density is nothing but a S into ID L by A. So we can say that current density increases by factor S. What? Current density increases by factor S. Means in small area, previously less current was there, but as the number of devices increases, so on the small area you will be having more current. So that is the meaning of this. So it is scaled up. Scaling on the current density in the constant field scaling, that in this way you need to remove. Just we need to replace all the parameter by S, W by S, W by S, L by S, VGS by S, VTN by S. So everything after putting this value, what you are getting? This. So here what is happening? Same way as you got in the linear current, that is drain current in saturation region is scaled down by parameter S in constant field scaling. As the voltage is also scaled down, so current is also scaled down by parameter S. That way you can relate. Hope the things are clear. Now, static power dissipation or instantaneous power dissipation. What is power dissipation? V into I. So here the definition is VDD into ID. Now VDD you need to scale down by S. ID is also drain current, which is scaled down by S, because we found it right now. So VDD dash is replaced by VDDS, and ID dash is replaced by IDS, as you got it over here. You can consider it as a saturation current or linear current, doesn't matter. So it is mentioned as a ID only. It is not mentioned linear or saturation. You can consider any one. Now, what is SPD? That is static power dissipation after scale down, which is put these values, and after that you are getting this. So just comment me in the chat box. Will over here power dissipation decreases or increases? Just let me know. Here, power dissipation increased or decreased? Just let me know. Yes. Yash, Prajakta, Mayuri, Anjum Fija, Snehal. Yes, you are right that it is decreased by what? It is decreased by factor S square. So just think that we are targeting VLSI design, VLSI devices like PDA. Power dissipation should be less, delay should be less, and area wise it should occupy less area. So we are targeting this, that this particular power dissipation decreased by or scale down by factor of S square. Hope the things are clear. Okay. In the same way, you are having the things over here also. Power density, that is PD by A. How to find PD? That you already got. It is decreased by S square. So we have replaced this PD by PD dash. And A is what? That is A by S square. Replace that. You are getting the value. What you got over here? There is no effect of power density. There is no effect of constant field scaling on the power density before and after the scaling. So both are same. Okay. On resistance, same way you can find resistance is nothing but V upon I. So VDS is taken and ID linear is taken. Replace that value accordingly. So here also you are able to see there is no effect of resistance, no effect of scaling on the value of resistance before and after scaling. Okay. Now here just I want to concentrate delay. What is meant by delay? That is RC time constant. You are able to see this diagram I have pasted over here, R and C. Okay. Now, if this is my one gate CMOS circuitry and this is second gate, that is the CMOS inverter. So output of this is acting as an input to this. Okay. So just consider CMOS inverter as this is the gate I have drawn. This is the CMOS gate. So here we have connected PMOS and NMOS. Here also we are connected PMOS and NMOS to form the inverter. Now output of this is connected to input of this. So can I say output capacitance of this is nothing but input capacitance of this? So I can say CL is nothing but a CG. Is it clear? We are connecting load capacitance over here because to have a load. But as we have connected this another inverter over here, we can say my gate capacitance is acting as a load capacitance to this first inverter. Okay. So that's why here it is replaced by CL is replaced by CG. Okay. Is it clear? Yes. Thank you. Now, as T equal to R on into CG, R into C. So we have replaced the thing, and after replacing, what we got that T after scaling, constant field scaling is what is happening. Is it improvement you are able to see or deterioration in the characteristic of the device? Just let me know. The device is improving, circuit is improving or deteriorating because of this scaling. Just let me know in the chat box. Speed increase हो रहा है कि decrease हो रहा है? Just let me know. Yes, thank you. You are attentive and giving answer. Thank you. So it is improving because previously time was T. Now time was scaled up. यहाँ पे क्या हो रहा है? Your time is we can say T by S. It's scaled down. Less time में आपका circuit perform कर रहा है. Means less time is required to give the output, and that's why it is more fast because frequency is opposite to time. So if time is decreasing, means frequency of operation increases. That way the circuit is become more good, or it is improving. So hope the things are clear. This performance is increasing, performance is improving. So hope the idea is clear behind this. So now the same way frequency is what 1 by T, and where the time is reducing means time required to give the response decreases, means the frequency of operation increases. So this will become more fast. So what you are able to say that after scaling frequency, what is the effect of that on frequency? The speed increases. The delay got reduced by S, so frequency increased by S. Previously it was working on 50 hertz. Now it will be operating on 100 hertz. Likewise, speed of operation increases. Now next like is the dynamic power dissipation, DPD. So what is that? Dynamic power dissipation. We have studied that equation. I told you to actually derive that equation. VDD square into F into CL. That is the dynamic power dissipation because of charging and discharging of capacitor. Hope you are able to recall. So VDD square into F into CL, where CL is nothing but a CG, and value related to CG dash we have already find it out. So after putting these values, what you are able to get, that previously deep dynamic power dissipation was DPD, that denoted by DPD, but now because of constant field scaling, your dynamic power dissipation decreased by S square. Means पहले ज़्यादा था, अभी क्या हो रहा है? Because of this, it is reduced. And same we want that power dissipation should be less. So in this way, we can say our circuit is improving. Our device characteristics are improving. Hope the things are clear in your mind. Okay. So power dissipation decreased by factor S square. Okay. So moving towards the next point. Same way what we did, we need to do it for constant voltage also. Now just see this particular diagram. What you are able to see here is the supply rail present. What is meant by supply rail? That from which you are supplying the power. Okay, so here is the IC. Inside that IC, there are different components placed, and there is the internal circuitry. Okay, now it is not like that every component operate on same voltage. Some circuit requires 1.2 volt, some voltage circuit requires 5 volts, some requires 12 volt. So every time if you need to have a different voltage, it is difficult, and that way what will happen, you need to have a level shifter or voltage divider circuitry to be present on this particular sorry, voltage divider or level shifter circuit is required for the operation of the different component or circuits over here. And that is the biggest drawback of constant field scaling. What is happening in constant field scaling? All the voltages are scaled down, and that's why you need to apply different voltage for different components. And to do so, we require different voltage divider or level shifting circuitry. And it is somewhat biggest drawback of constant field scaling. Hope the things are clear, because you require different voltage, because every time voltage are scaled by factor S. So previously it was 5, now it will be divided by 2, suppose, so it is 2.5. In some technology it will be 1.25. Likewise, everywhere you need to have a different voltages, and for that you require level shifter circuitry. So that way circuit become again requiring other circuit. Okay, so now moving towards the next point. Hope the things are clear. Now, what is constant voltage scaling? We will be going fast now, because same way whatever we did in the constant field scaling we need to do. So that is I'm giving as a self study for you. Just to give the overview, I'm just telling here what are the dimensions which we are scaling down, that is other than VDD and VT, that is voltages. So here all the things, all the parameters are scaled down by S, but VDD will be kept as a VDD, and VT will be kept as a VT. VGS will be kept as a VGS. VDS will be kept as a VDS. Will not be changing anything over that. Okay. So now what to do? Here you are able to see same way. Now in constant field scaling, we have seen this. There is no components such as VDD present over here or voltage is present over here, and that's why this value will be same as a constant field scaling, because TOX is scaled down here also. So wherever there is a voltage term coming, that value will get changed in the constant voltage. Rest of the things will be same like a constant field. Again, you are able to see CG. Here, is there any voltage term coming? No, means there will not be any effect of change in the previous constant field scaling. Okay, CG dash equal to CGS, CG by S. But here, just see current in linear region. It is related to what? VGS, VT, and it is related to VDS. So here in constant voltage scaling, what we are doing, we are keeping this as a constant. We are not changing it. We are not scaling it down. And that's why, although it is mentioned as a VGS dash, it will be VGS only. It is not VGS by S. In previous constant field, we have scaled down this voltages also, but here we are not scaling it down. And that's why what is happening, after putting this value over here, what you are getting, linear current, drain current in linear region is increased by factor S. Previously it was reduced by factor S. Here it is increased by factor S. So in the point of gain will be more over here. And in previous constant field scaling, gain will be less because current value is also decreasing. Hope the things are clear. So I'm going fast from this point because I need to recall the things only. Here junction density. What is junction density? It is related to ID by A. So ID is what is affected, that is S into ID. Previously in constant field it was ID by S, but here now it is increased by factor S. So what is the value of current density? In smaller area, what current is it is handling? That is S cube. So huge current will be handling. So that's why the circuit will become more heat up, and that's why current sink is required. Other again, as the device becomes shrink, so wire thickness will be less. So current flowing through that particular wire will be of short, having less thickness, and that's why this amount of current is carried by this particular wire, and that's why it will get wear out. It may happen like that because the thickness of wire is reducing, but the amount of current density increasing. So this is the biggest disadvantage of constant voltage scaling. Understood? So before going forward, I'm launching next poll. Yes. Are you able to see it? Do it fast within 20 seconds. Give the answer because I need to go to the another point also. In constant voltage, I am talking about constant voltage, which is partial scaling, where voltage is fixed constant, kept constant. Most of the students are giving wrong answer. Read the question twice. Don't get confused. So I am closing this poll within 5 seconds. 5, 4, 3, 2, 1, close. So in it will increase by factor right answer. Okay, so I'm closing this poll. Sorry. Hello, madam. So over here, you are able to see the things same way it is mentioned. Just here, constant voltage is kept constant instead of scaled down by S. It is kept constant, and because of that, saturation current is also improved or increased by factor S. Static power dissipation, you are able to see the static power dissipation increased by factor S. So this is the again a drawback because power dissipation increases over here. Okay, as the voltage is kept constant, definitely it is going to increase the power dissipation. So answer question I have asked, it is power density. So as the current density is thrice S cube, so it will be also S cube times of previously, means it is increased by S cube. Okay, on resistance previously for the constant field it was same, but here it is reduced by factor S. Related to this, time, again it is more time efficient, and frequency wise it will be what the speed of frequency of operation increases by factor S square. So operation wise it will be faster, but power delay is more in this particular type of scaling, constant voltage scaling. So again over here dynamic power dissipation also increased by factor S. So just go through this particular thing. It's now over here you are able to see some parameters we have written over here. Power dissipation in full scaling reduced by S square, but here it is increased by S. Here current decreased by factor of S, but here current increased by factor of S. Here most important thing, that is the power density. It's what is the, it is what is the power by area. It's not affected, but here it is increased by S cube. So this is the biggest disadvantage of the constant voltage scaling. Okay, current wise current is improved, that is increased. So gain wise gain will be more in this type of scaling. Okay, now main thing, that is the problem. that is gate tunneling. As I discussed this in the hot electron effect, as the gate thickness decreases because of scaling down of the device, what will happen? At the gate thickness is less, electrons are more energetic, and they will rupture the oxide thickness, and it will have a current flow, that is gate current is flowing. Actually that gate current should not be there, it should be zero, because there is an insulation, and because of that there is a high input impedance. Because of the electrons, hot electrons is rupturing that particular TOX layer, and it is going through that gate, there is a gate current, and it decreases the input impedance as well as it damages the device. So that is happening because of this scaling. Electromigration. Previously the thickness of the wire is good enough to carry the current, but now because of scale down, the wire length is also reduced, and it has to handle the high current. Because of constant voltage scaling, you have seen that it is current density is increased by, current density or power density is increased by S cube. So it is not this particular thin wire is not able to carry that particular amount of current, and it may get wear out or it may get break. So that are the problems might coming because of the scaling. So you need to take a proper decision while instead of you, the proper care will be taken by the manufacturer to see what are the things required, and better option will be chosen.